The purpose of this video is to talk about some of the functions that are provided by the DBMS, how it handles updating and retrieving data. We're going to talk about this thing called the catalog. And we also need to discuss this thing called concurrent update and some of the problems that can introduce and how the DBMS handles the problem. And then we're also going to talk about being able to do data recovery and how that process works in a DBMS. The basic functions of a DBMS are simply to update and retrieve data, which we've done throughout the semester whenever we use a SQL statement. We're going to provide catalog services. We need to be able to support what's called concurrent update, which we'll get into more in just a little bit. We need to be able to recover data when a problem arises. We need to get our data back from a backup. We need to be able to provide security to the database and also to the data. We want to be able to provide data integrity, so therefore we want to make sure that the data that gets written actually is correct. We need to be able to support what's called data independence and data replication, and this is all going to be done through what's called utility services. Now, we obviously use the DBMS anytime we want to retrieve or update data from the DBMS, and like I said, we do that with a SQL statement. Users don't necessarily need to know how the data is stored. All we need to know is that we are going to issue a particular command to actually be able to get the data or to update the data. Our users are going to add, change, and delete records during normal updates. Now, the normal flow is that we're going to have a user that's going to ask for data. In this case, this user wants to enter a new part. Then what happens is he or she puts that into a form or something where you want to actually update the database. We send it to the DBMS. Remember, the DBMS is the only thing that's allowed to actually talk to the real database. The DBMS turns around, checks to make sure that part really doesn't exist. It doesn't, so therefore it allows the part to be created, and then it sends back a response. So the DBMS, as far as the user is concerned, the user will only ever talk to or receive information from the DBMS. The user will never get to talk to the actual database. Update process, what we're going to do is we are going to send information. So in this case, we're going to request information for this particular part. We send it to the DBMS, and the DBMS has to go through another process before it actually will respond to us. So what happens is the DBMS talks to the database to get the information for it, and then that information is sent back and replied to the user. So the user is giving confirmation this part exists. Then the user turns around and wants to make changes to it. So the user sends a change to the DBMS, and then the DBMS turns around once again and actually sends a message to actually change the database. And then the last thing that's missing from this is that the DBMS will turn around and give a confirmation to the user to let him or her know that was actually done successfully. Now we're going to start off with another basic example here. We have users asking for the balance for all season. And then what happens is we send that request to the DBMS. The DBMS turns around and says, hey database, what's in there? The database will actually provide the information for the DBMS. So it gets the information and then it sends that balance back to Elena. What we're going to do is we're trying to talk to the database, and we need to know some things about it. We need to know what's stored in it. So we're going to use what's called metadata. Now, metadata just simply is data that describes how the data is actually organized and stored in the database. So this is going to be things like what are the tables, what are the fields, what are the relationships, any views and indexes, our users and privileges, any replicated data. And then the metadata is what's used to actually make it where the user can talk to the database. So what happens is our metadata is used for us to be able to describe to the system how stuff is stored. So therefore, when I actually go to perform a query, it's going to look things up in the database. Well, it has to know, does that table exist? Does this view exist? Does this relationship exist? And then what we do is in enterprise environments, we actually have what's called a data dictionary, which is what's called a super catalog. And it's just simply a much larger listing of all the metadata. So we have a list of all the databases, all the tables, all the users, and all of the systems that we have. And we just call it a data dictionary. Our DBMS has to be able to support what's called concurrent update, and this ensures accuracy when several users update the database at the same time. So far, what you've worked with this semester is one user performing one query at a time. The problem that we encounter is called concurrent update. This is when we have multiple users that are making updates to the same database at the same time, usually when they're trying to make an update to the same record at the same time. All right, so here's our problem. We have a user named Ryan, and Ryan is trying to look at this database, which is on the disk. Elena is also trying to get information. All right, so if we have one user trying to get information, no problem. So Ryan is looking at the database, and Ryan says, hey, what is the balance for this particular account? The DBMS will turn around and will respond with $431.50. So what happens is Ryan's computer has to load that into memory. Now, what happens is there is no connection to the database here. We're just simply asking it, what's the balance? It tells us the balance, and then our computer thinks that the balance is $431.50. So then what happens is we change the balance in the memory on the computer, and then we turn around and provide an update query where we update the balance to $531.50. No problem. We added $100 to the account. The user's happy. The money's there. All right, we have Elena over here is going to ask the database what the balance is. Balance is $531.50. So Elena loads that $531.50 into memory, performs some calculations on it. So in this case, we're going to subtract $100. And so now Elena will turn around and tell the database, hey, the new balance is $431.50. The database doesn't know the calculation that was performed. The database just strictly knows what the resulting balance is at the end. So here's the problem that we have. When we have a record that gets updated and two different people are trying to do it at the same time, then we run into a problem. Okay, so what happens is here, in this case, let's say Ryan is trying to add $100 to this account. All right, so what happens is Ryan says, hey, what is the balance? And the system sends back $431.50. Before Ryan can do anything to update this, Elena also asks the database, hey, what's the balance? It says $431.50. So if you'll notice in memory on both of these computers, it says that the balance is $431.50. Okay, now what Ryan does, Ryan turns around and says, hey, I want to add $100 to the account. So it tells the system, okay, the new balance is $531.50. Great. But Elena still thinks that the balance is $431.50. So if Elena tries to perform an update on it, she will actually override whatever Ryan wrote to the database with this $431.50. So that $100 deposit just got lost. Okay, extended a little bit further, if we look at this example, we have $531.50 because remember Ryan was adding $100, Elena was subtracting $100. Now Ryan thinks that the balance is $531.50, that's what it told the DBMS. Elena thinks that the balance was $431.50 and takes $100 off, which means that the new balance is $331.50. Elena turns around and tells the system here, Ryan updates and says, hey, the balance is $531.50, they deposited $100 in the account. Great. Elena still thinks the balance is $331.50 and turns around and updates the system and tells it $331.50. Now we're missing $200 in our account because we allowed two users to manipulate the same record at the same time. So the question is, how do we fix this? All right, so the way that we used to do it is what's called batch processing. This is still done somewhat, but for the most part, we've gotten away from this. Batch processing was kind of like having a register in your checkbook. And what this does is throughout the day, we do all of our credits and debits on the account. So we add all of our money, we subtract all of our money, and then what happens is at the end of the day, the system will process all of those in order based on a timestamp. And only one program, the one that is actually doing the batch processing at the end of the day, is actually allowed to update the database. Now what happens though is this only runs at certain times. And typically when you think of a bank, banks do this all the time because they will do their update at night when nobody's actually at the bank. That's why when you look at your bank account receipt, anytime you deposit money, it'll say something like current balance is this, but available balance is this. And the reason for it is because your available balance is based off of the actual database. The current balance is based off of the register where you actually did the deposit or the withdrawal. The problem is this data very quickly becomes outdated. So if, let's say I deposit money in my account today, I deposit $200 in the account, and I need to immediately use that $200 to pay a bill, and my bank uses batch processing, that $200 may not be available to me to actually make a payment right now. So the problem is that this will not work in situations where we require the data to be current. The better way to handle this is what's called two-phase locking. And what two-phase locking is just simply that we put a lock on the entire record or even an entire table, depending on the system. And then we just simply state, hey, I'm doing something with this record or with this entire table. Nobody else is allowed to touch it until I'm done with my transaction. And a transaction is going to be the set of steps that's required to complete the entire task. So if you think about the task of adding $100, first thing is we have to ask the DBMS what's the current balance. Then we have to perform some calculation to figure out how much money we're adding or subtracting from the account. Then we have to tell the database what the new balance is. And then the last step is that it actually has to be what's called committed. And commit is kind of like telling the database, hey, I'm done with my transaction. Here's the real balance. All right, so we have what's called a two-phase locking. And a two-phase locking just simply means we have a growing phase where we lock the database, or we lock the table, we lock the record, and then we can lock more and more and more rows to determine which all ones we need. Okay, so what happens is this growing phase is, okay, I need a record from this table, and I need a record from this table, and a record from this table, and so we're just grabbing all the records that we need, and then we try to lock them all. All right, so now what will happen is when we're done locking them, in reverse order, we have to release the lock. So that's called the shrinking phase. So we're just simply releasing all of the locks on all of the records that we put the locks on. All right, so that looks something like this, which is Ryan is doing something with the database right now. And when Elena tries to get into the record, even to perform a query to see what the balance is, she can't do it. She'll get some sort of error that the record is locked. Okay, so Ryan's still in the system. He's doing stuff. She still gets this record is locked. And then Ryan is finally done. He commits it to the database. Well, Elena has to wait until the entire shrinking process is done to be able to get into that record. All right, so now once he unlocks the record, now Elena can get in there and she gets the balance. Now Elena removes her $100 from the account, and the balance was $531.50 after Ryan added the $100. Now she subtracts the $100, puts the balance to $431.50, and then we end up with the correct balance. So by locking it, what we do is we prevent somebody else from getting the balance, and then that way we can prevent somebody from accidentally writing the wrong value to the database. The problem that you can encounter with locks are what's called a deadlock or a deadly embrace. And just simply what this means is that I have a lock on one record and a lock on another record. All right, so if you think about this, I have a lock on a record for a dishwasher and a lock on a record for a microwave. And I'm trying to simply update the total number of records or of quantity that we have for the microwave. So I lock the dishwasher, and then I go to try to lock the microwave, but somebody else has a lock on that. Okay, let's say the other person is trying to update the microwave and the dishwasher. Okay, so the other person put a lock on the microwave. The first person put a lock on the dishwasher. And then when they try to lock the other item, neither one of them can lock the second item. All right, so what this means is that neither one of them can do anything. They can't perform their transactions. And essentially what would happen is the system would come to a halt because nobody could do anything with those records at all. So what happens is the DBMS has to detect that and has to break the deadlock. And the way that it does it is it will randomly pick one of the two connections, and it'll pick a victim. And essentially what it does is it takes whatever updates that person did, and whichever ones were committed, it will undo those. It releases all the locks on them, and then gives what's called a standoff or a step-off period, which is just simply so many milliseconds that the second computer has to wait to try again. So what happens is the end user won't notice anything. The end user just noticed that it took a little bit longer to perform that transaction. But what happens is the system behind the scenes handled that deadlock. It prevented data from being locked up permanently, and also prevented somebody from updating one record without getting to update the other one, which could lead to inconsistent data. Now, if we talk about a PC-based DBMS, really what we're talking about is something like Visual Fox Pro or Access or DBase or something like that. These are going to be a little bit more limited. Usually what happens is we can't lock one record. We usually have to lock the entire table. So what happens is when I want to do something in Access, Access will lock the entire table when I try to perform an update query. So what happens is my computer has to tell Access that I'm trying to perform a transaction. It has to start the transaction, and then it has to tell it when it's done, hey, the transaction is done, and then Access will lock the entire table. When my transaction is done, it'll release the lock in the entire table. Another way to prevent these update problems where we have the lost transactions is to use what's called timestamping. And what a timestamp does is it puts a unique date timestamp on each record whenever it's added to the database. And what this is kind of like a combination of batch processing and our two-phase lock. So what happens is the record, when it gets written to the database, the system will automatically add a timestamp column to every single record that's there. Now by default, MySQL does this for us. Some of our other systems we have to manually turn it on. But what happens is by doing the timestamp, now what the system can do is it can say, okay, well, we had two different people that tried to update the record at the same time. Which one of these two updated it first? And then the system will know that the second one was wrong and it will try to reapply it. So in the case of Ryan, what it'll do is it'll do Ryan's transaction of adding $100, and if Elena at the same time tried to subtract $100, then the system will say, hey, hers needs to stop. We're going to delete that update from Elena and then force Elena's computer to do it again. The advantage to this is that we can avoid having to lock the rows, which means we release some of the processing time that is required to perform the locks and then resolve deadlocks. The disadvantage, though, is we're going to require additional disk and memory space, because what happens is the system is going to have to write every single record that we try, even if there's one where there was a lock, or not a lock, but even if we had two that were conflicting, it'll still have to store those on disk. So we will end up using more disk space. We will use a little bit extra processing time to process those extra queries. However, we didn't actually have to use processing time to lock and unlock the tables. All right, so one of the other things we need to be able to do is recover data, and databases can be damaged very easily. All we need is the user to enter data that's incorrect, overwrite something, delete something, accidentally issue a query that somehow removes an entire table or a record. We could have transactions that end abnormally, and when we have an update that ends abnormally, it can lead to an inconsistent state. We could also have a hardware problem, so if we have a hard drive that fails or something like that. So the process of recovery is just simply returning the database to a correct state. And the simplest way to do it is to use backup. So we back up our database, and what we can do is we can just simply make a copy of our entire database. The problem with that is that when I do a backup of the database, we have transactions that occur after the backup. The other problem that I have with that is we can't directly save files. So it's not like a Word document or something like that where we can just simply make a backup copy of it, and here we have two of them. No, the problem that we have with the database is most of our databases can't be backed up while they're online. To fix this problem, we're going to use a process called journaling. Okay, so I'm going to use an analogy here. And my analogy is going to be, think of a secretary that has an inbox on the desk and also has a filing cabinet. Now the inbox is going to be like a journal, or what we're going to call a log. And then the filing cabinet is going to be the actual database. Now what happens is throughout the day, every time somebody wants to perform a query to the database, they have to, if I want to do an update on the database, I'm going to perform an update, I want to change somebody's balance, what I have to do is I have to fill out a piece of paper. And I have to fill it out and say that I want to change the balance for a particular account to so-and-so. All right, so then what we do is we take the piece of paper, stick it in the inbox. Now, the secretary's not going to touch it. The secretary just leaves it. Okay, so throughout the day, all of the users come in, and every time they want to update a balance, they have to add another piece of paper, and the papers just get put on top of each other. All right, so somebody comes through in the middle of the afternoon, and they say, hey, I want to know the balance for Joe Smith. Okay, so what happens is the secretary will have to look in the filing cabinet in the actual database to find Joe Smith's record and get the balance. But the problem is the one that's in the filing cabinet in the database is not correct, may not be correct. Okay, so then the secretary has to go through every single one of those pieces of paper to see if Joe Smith's balance was updated. Okay, so if the secretary goes through the papers, and the secretary has to start at the bottom of the stack, go through one at a time, and see all of the times that Joe Smith's balance has been updated. All right, so this is going to be very inefficient. It's going to cause the system to slow down quite a bit. And that stack on the secretary's desk is going to grow bigger and bigger and bigger and bigger. Okay, problem. How do we keep the stack from getting too big, and how do we cause the system to get slow? Because what happens is, as that stack gets bigger, it takes longer and longer to perform queries because we have to check the database and we have to check the log to see if there are any additional records that have updated the particular record for Joe Smith. Okay, so what we're going to do is we're going to keep track of what's called a transaction ID. We have the date and time of the update. We store what's called a before image, which is going to be what was the balance before I changed it? What is the balance after I changed it? And then what we do is we start the transaction and then state on our piece of paper if we actually were successful. Okay, so the problem is the stack's getting bigger and bigger. How do we fix it? All right, well, the way that we do it is we go through this process called truncating the database. The truncation process, though, only occurs during the backup. And what the truncation process is imagine taking out Joe Smith's record from the filing cabinet, going through every single little piece of paper that's on the secretary's desk, figuring out what Joe Smith's balance really is, writing it on the record that's in the filing cabinet, and then putting it away. And then do that for every single customer. But then what you can do is you can start getting rid of those pieces of paper that have all of the balance updates for Joe Smith. And now at the end of this process, our inbox on the desk should be empty. So the filing cabinet is the database. That's our actual production environment. But we also have the inbox, and we have to go through every single one of those pieces of paper. And by doing that, we're going to cause the system to go slow. Why are we doing this? Because we can actually back up our database, and we can keep all of the transactions that have occurred since the backup. Remember how I said that the system keeps the before image and the after image for each one of those pieces of paper? That process will allow us to simply make a backup of our database from yesterday. Let's say our backup occurs at midnight every night. And then throughout the day, we've had all these pieces of paper that were put into the inbox. And what happens now is I don't have to keep doing backups of my database throughout the day. I just simply do backups of the log throughout the day. Okay, so the database itself is sitting there, never gets touched. We never actually do a backup of it throughout the day. We do at night. But what now I can do is I can take the database, if it gets corrupted, I can restore the database, and then what I can do is I can go through all of the pieces of paper that are sitting in the inbox, and I can reproduce all of the transactions that have occurred throughout the day, and I have not lost any information. It's all there, it's all current. The only problem is going to be that we have to wait for the system to go through and actually update all those records. I also said on those pieces of paper there was a before state. Now the before state is going to be used if, let's say I go through the records throughout the day and we find out that one of our records failed and it corrupted Joe Smith's record. Then what we can do is we can go back through that stack and look at the before image and see what his balance was before I tried to perform that transaction. And then what that means is that we can go back and put his balance back to the way it was before I messed up his balance. So we're just simply going back. The backward recovery is like an undo, and we're just simply undoing our changes so that way we can go back and put it the way it was before we mess something up. Now, the journaling is only going to be in your better systems, so it's going to be MySQL, Microsoft SQL Server, Oracle. Your high-end DBMSs are going to support that. Things like Access, they're not going to be so sophisticated. What you're going to have on Access is just simply make a copy of it. Now, Access, it really is just one file that you're going to make a copy of, and just store it on your flash drive or store it on a CD or DVD or on online storage, wherever you need to put it. But in Access, you just simply keep making copies of it just like you would with a Word document. Databases also provide security services. Now, this is the prevention of unauthorized access, whether we allow somebody to get into the database on purpose or if we don't want somebody in there. All right, so some of the more common features are going to be things like data encryption, authentication, making sure we have the right user, authorization, once we know we have the right user, what are they allowed to do, and then also the use of views. Now, we've talked about views before, where we can use these to actually provide a limited view of the database, so that way somebody that only needs a small portion of the information from the database only gains access to that portion that they actually need. Now, encryption is converting the data into some format that is indecipherable by another program, and we're going to store it in an encrypted format, which means when you actually look at it on the hard drive, it'll be encrypted, which means if somebody else gets a hold of our file, they can't read the data that's in there. Now, in the security fundamentals class, we'll actually talk about how this works more in depth. But what we can do is we can do things like we can encrypt it, we can salt it, we can hash it, and what we can do is make it where somebody else cannot get that data out of there unless it's on our system and they know our key. Now, as far as the end user is concerned, they won't notice any difference, except encrypting data requires the user to decrypt it, which means to reverse the encryption, and that just simply is going to take some extra processing time. So encrypting and decrypting the data will take a little bit extra time, and it will be a little bit slower. In Access, the only way to encrypt the database is to simply put a password on it. Authentication is going to be the different techniques that we use to try to verify who the person is. The most basic one that we're used to using is a password. That's going to be some sort of string of characters you have to enter. We have biometrics. That's going to be things like your fingerprint, a voice print, handwritten signatures, facial characters, or characteristics. We have other things that we can use too, such as the new infrared cameras, but we can figure out who a person is and only allow them in based on who they are. And then we also have what are called smart cards, which are going to be just a small plastic card, looks like a credit card. And you either put it in a slot, or in some of the computers, they're even contact cards, which means you just simply set the card on the computer or touch it to the computer, and that will allow you to get into the system. In Access, we have a password. You just simply enter the password, and there you go. We're into the system. So Access is very limited in what it actually allows us to do for encryption and also with authentication. Authorization is going to be, once I know who you are, then I need to figure out what you're allowed to do. All right, so we have permissions. So are we allowed to view things? Are we allowed to update things? And then we can also assign people to groups of users, and these are actually called roles. And so what I can do is I can assign a user to a role of backup operators or update operators or system admins. And then what that does is it allows me to assign permissions to the group, and then anybody that's in that group will get the same permissions. Now, we talk about this in other classes, but we also have to worry about privacy. And remember, privacy is nothing more than the right of individuals to have certain information about them kept confidential. All right, so when we deal with things like health insurance or with you as students, we have to worry about the confidentiality of the data that we have. There are laws that protect you as a student. There are laws that protect you as a patient. All right, now this differs from security, but it's related. What we're doing is we are trying to use security, our passwords and our encryption and our authentication and authorization, stuff like that, to figure out who you are. And then we use that to try to ensure some level of privacy. Now, like I said, there are laws that regulate how we handle privacy. So you make sure whatever industry you're going to work for, that you know what those particular laws are. But then companies will also have additional privacy rules, and then all of the employees have to adhere to those. We need to provide data integrity. Now, these are going to be rules that are followed to ensure that the data is accurately and consistently updated. These are going to be things like our key integrity, our foreign keys, primary key constraints. So, for example, here we have a rep number cannot be used for somebody else. So that way we make sure that we never have two customers that have the same rep number, but it's actually two different people. We don't want that kind of stuff to happen. We also need to ensure data integrity. So we know that the data type, if it's text or a number or a Boolean or whatever, we have lists of legal values. So if we have credit limits and our credit limit is either 1,000 or 1,500 or 2,000 or something like that, or we can format things so we can state that it must be 4 digits, 2 letters, and a number or something like that. Now we can implement these integrity constraints, but then we can decide how the system can handle it. There's 4 different ways that could happen. The first one would be we create a constraint, but we really don't care. So we can tell the system that we're going to ignore it. So if somebody tries to break a constraint, no big deal, just ignore it. So what that means is the data may be invalid, but it really doesn't matter. So what we can do is we can put the constraint enforcement on the users. So we could tell users, hey, you need in this particular field to put a number. It can't be a word or something like that. We just simply leave it up to the users. Well, we can almost guarantee that the users are going to do that. They're going to put something in there that shouldn't be. All right, so we could leave it up to the programmers. We could tell, hey programmer, make sure that your program can't put the wrong type of data in the database. That's not necessarily feasible either. The best way to actually do this is going to be for putting enforcement for constraints directly on the DBMS. This is going to be our best means of handling integrity constraints. Our databases need to be able to support what's called data independence, and what this means is that I should be able to change things in the database without breaking the application. I should be able to change things in the database without breaking any programs that actually want to talk to the database. Now, the easiest way to do this for data independence is to get in the mindset that we don't ever want to delete a column. We can add columns, but we don't want to delete one. We also don't ever want to change the data type for a particular column. The reason for it is if I have a program that's looking at that record, or I'm sorry, at that column, and that program expects a specific type of data type, and I change the data type, then I've now not only broken my database, I've broken all of the other programs that are going to talk to it. So things that we need to really take into consideration is whenever we add fields, if we change fields, if we create indexes, or if we change relationships, that kind of stuff can very easily break other programs. Generally, changing the length of a field will not cause a problem. It won't break things. Unless, and here's the time that I've seen it happen, there is a data type called a character data type. And a character data type allows us to have a string in there. But the thing is that a character data type, if I tell it that my character data type field is 14 characters long, that has to be exactly 14 characters long. And what happens is most of your DBMSs that we use the character data type will pad those with a bunch of spaces at the beginning of that text string. So let's say I type in the word Bob and it's 14 characters long, then what it will do is it'll take 11 spaces and apply those before Bob. And then what happens is later on, if I try to say something like, if the name is equal to Bob, then, well, that's not true because it's not equal to Bob. It's equal to 11 spaces and then Bob. All right, so one of the things we need to keep in mind is if we change the length of the field, make sure it's not one where we have data that's padded. Our database also needs to be able to support indexes, and an index is just simply used to provide another way to search through the data in our database. You use an index anytime you do a search online. Whenever I do a search, I type in some things, and the index is just simply going to be a list of all of the fields that the system has previously optimized for me to actually be able to perform that search. It's necessary for our database to exist at multiple locations for efficiency, and this is going to be things like where I have an office in New York and another one in San Francisco. I don't necessarily want all of my data going through the data lines. So what we'll do is we'll replicate the database at 2 different locations, but now we have a problem where we have to manage the multiple copies of the same data in multiple locations. All right, so how do we do this? We could use what are called replicas, which is just simply a copy of 2 separate databases. Or we could do what's called synchronization. So we actually have a database at one location that's our master database location, and then we have some backup computers that are going to be also having a copy of that database, but then they work as kind of like a slave. And what happens is anytime a record is written to any of the DBMS servers, it'll automatically turn around and send that information out to the other servers, so that way they're all updated at the same time. Yes, we're using more bandwidth this way, but the bandwidth is only used for actually performing updates, not for every single user request that comes out of the database itself. The DBMS also has to be able to provide what are called utility services. This is going to be things where we use or we do general database maintenance, things like changing the database structure, adding new indexes, deleting indexes, using services that are available from the operating system. So if I want to import files, if I want to read data out of an XML file, that all comes from utility services. So we're going to be able to use utility services also for doing things like editing query capabilities, screen generators, reports, and things of that nature. Utility services comes in when we start dealing with our programming languages. So we've talked about SQL as a non-procedural language. So a procedural language is going to be one where we have to tell the computer do this step, then do this step, then do this step, and so forth. And things like BASIC, Visual Basic, C++, C#, COBOL, they're all procedural languages, but they do also support what's called object-oriented programming languages. A non-procedural language, though, is going to be one where you tell the computer, I want you to perform a task, but I don't tell it how to do it. SQL is going to be one of those. So I tell SQL, I need you to get the telephone number for Bob Smith, but I don't care how it does it. All I care is that it actually goes and gets the information and provides it back to me. In this lesson, you learned that the DBMS allows the user to update and retrieve data in a database without needing to know how the data is structured on the disk or how to manipulate it. The DBMS has to store metadata, that's the data about the data, that tells the system how the data is actually stored in the database. So it's a list of all of our tables, all of our databases, all of our views, keys, things of that nature, but the metadata is not the actual data that's stored in the database. The DBMS must be able to support concurrent update because we don't want those update anomalies that are caused by two users trying to update the same field at the same time. We use locking to deny other users from gaining access to a particular record or an entire table. However, our locks can cause a deadlock, and in which case the system is going to have to pick a victim, kill off one of the victims, and tell that user's computer that it has to try the transaction again. Instead of using locking, we can use timestamping, and that allows us to process the updates in the order that they were actually committed to the system. It does use additional processing time for those additional records, and it also uses extra hard drive space, but it makes it where we don't have to lock the database. The DBMS has to be able to provide methods to recover a database in the event of damage. It has to be able to provide facilities for making the backups. And remember, we talked about the journaling as a means for being able to do backups and recovery. And then also our enterprise class DBMSs, the log or the journal, is going to be all of the updates since the last backup has occurred. The log is used for the recovery process, and when we do our backup, the database gets truncated. The log gets truncated, which means that the log gets committed to the database, and that's the point when the data is actually fully committed to the database, and the only place where the data exists is in the actual database. The DBMS provides security features, so it has encryption, authentication, trying to figure out who the user is, authorization, what is the user allowed to do, and views, that's where we make up our own fictitious tables in the database, so that way the user can only see certain things. The DBMS is going to have to follow the rules or integrity constraints, so those are going to be our key constraints, data integrity, so that way we can make sure that the data that gets updated is accurate and consistent. Make sure you know that it's up to the DBMS to provide those constraints. It should not be up to the users or programmers or somebody else. The DBMS does have to be able to support data independence, which means we can make changes to the database without breaking things. We do have facilities to handle data replication, so having the data in more than one location. And then utility services are going to be able to provide general maintenance to our database.